So we're going to move on to section 8.8, and this won't take too long, and then after that we're going to do a little bit of section 8.9 and get ready to finish up the unit. So we're looking at section 8.8, which is on page 30 in your packet. And we need to talk about these things called natural logarithms. I mentioned those much earlier in the unit, but we need to come back and redefine them and then see how to use them. A natural logarithm, let me zoom in a little bit more. A natural logarithm is just a logarithm with a base of e. A logarithm with base e. Focused. A natural logarithm is a logarithm with base e. So, for example, letter A is asking us to find the natural logarithm of 2. The log base e of 2. E raised to what power would give us 2? Well, there's a button on your calculator for this. On your calculator, find the button that says ln. On the graphing calculator, it's right below the button that says log, and it's on the same button as the e to the x key. And I'm going to type in the natural log of 2. And I'm going to get about 0.693. And I'm going to round these things to 2 decimal places. 0.693. All I did was I went to the calculator, used the ln button, and typed in ln2. You go try the natural log of 43. And if we're rounding to 3 decimal places here, that should be 3.761 for the natural log of 43. Well, we're going to use natural logarithms to solve certain types of exponential equations, and then we're going to see in the next section that it will be used to deal more with that compounded interest that we looked at a while ago. First of all, I want to solve the exponential equation e to the x equals 20. Well, we're going to do exactly what we did in the last section and rewrite this problem in log form. Log base e of 20 equals x. Log base e of 20 equals x. But log base e of 20 is the same thing as saying the natural log of 20 equals x. Log base e of 20 is the same as saying the natural log of 20. So, we're just going to go to the calculator and type in the natural log of 20, and we should have our answer. I think this is about 2.996. If you do want to check this, not that you have to check for extraneous solutions, but if you go to the calculator and do e raised to the 2.996, you should get something pretty close to 20. Yeah, I'm getting 20.005, and if I used more decimal places than what I used over there, I'd get even closer to 20. We're going to rewrite these problems in log form, but then if our log is a log with base e, I can just use these natural logs to solve. In letter B, I'm going to say log base e of 7 equals 3x minus 1. And that means the same thing as the natural log of 7 equals 3x minus 1. I don't necessarily have to see the first step. I think it's helpful, especially because then it looks exactly like what we had done in the last section. But if you feel like you can go from the original problem straight to the natural log of 7 equals 3x minus 1, that's just fine. At this point, go to your calculator, do the natural log of 7, and you're going to get 1.946 approximately is about 3x minus 1. I'll add 1 to both sides. I'm going to get 2.946 is about 3x. And make sure, even though you're writing 3 places, that you're keeping the whole thing still stored on your calculator to make this as exact as possible. We'll finish this off by dividing both sides by 3. And we're going to get about 0.982. one more of these types of equations. In letter C, well, I first need to get the exponential piece by itself, which means we need to get rid of that 8. I need to get rid of the 8. So you're going to go and you're going to divide both sides by 8. You're going to get e to the 2x equals, I guess you could say 20 over 8, but why don't we simplify it down to 5 halves? See if you can take a moment and finish this one. Getting 0.458 from this. I rewrote my problem in log form. Log base e of 5 halves equals 2x, but log base e of 5 halves means the same thing as the natural log of 5 halves, which equals 2x. I typed that into the calculator, divided by 2, and got 0.458. So these equations we can call natural exponential equations because they have that e to the x in them. We now need to look at some equations that already have a natural log and see how to solve those. So we're continuing on to page 31. Natural logarithmic equations. We're going to solve the following equations and we're going to round the answers to 3 decimal places. The first one is the natural log of x equals 8. Well, a natural log just means a log with a base of e. So this means log base e of x equals 8. Haven't done any converting yet. I'm just rewriting what this problem means as it was written. Natural log of x means log base e of x. Now, I'm going to go and convert my log equation into exponential form, just like we did before when we had our log equations. I'm going to get e to the 8th equals x. You're going to go to the calculator, and this time we're not going to type in the natural log of 8. We're going to type in exactly what is written there, e raised to the 8th. So I'm going to do the second natural log thing, giving me e raised to the, it's a little bit tough to see on there, but I'm trying to do e raised to the. I'm going to raise e to the 8th power, and that should give you about 2,980.958. Natural log of x equals 8 meant the same thing as log base e of x equals 8. I converted that into exponential form, got e to the 8th equals x, went to the calculator, typed in e raised to the 8th, and got 2,980.958. Letter B. Well, that original problem with the natural log means the same thing as log base e of 3x plus 2, which equals 5. We're going to go convert this to exponential form. And I'm going to say e to the 5th equals 3x plus 2. Go to the calculator right now. Finish that one off. Getting 48.804. Letter C, before we do anything, we need to get our logarithm, our natural logarithm by itself. That means we need to go and divide both sides by 5. The natural log of x minus 1 equals 12/5, which means the same thing as the log base e of x minus 1 equals 12/5. If you feel like you don't need to write out this step, you're welcome to go straight from the original problem with the natural log straight into your exponential form. Going into exponential form, I'm going to get e raised to the 12/5 equals x minus 1. Go to the calculator. That'll give you 11.023 is about x minus 1. Adding 1 to both sides gives me a final answer of x is about 12.023. Last example in this section. In letter D, we have 2 natural logs. Well, like any sort of log equation, we can't handle dealing with more than one log in the problem. So if we have 2 natural logs, we're going to use our properties of logs to combine these 2 into a single log. When you add logs, remember, you multiply the stuff inside. So this is going to give us the natural log of 5x equals 9. Go from there. Getting 1,620.617. By combining the logs, I got the natural log of 5x equals 9. Well, natural log means log base e, so this is log base e of 5x equals 9. Go into exponential form, e to the 9th equals 5x. Type in e to the 9th on your calculator. You're going to get 8,103.084 is approximately 5x. Divide both sides by 5, 1,620.617. And again, I'm not dividing this number that I rounded by 5. I'm dividing the whole e to the 9th that's still left on my calculator, dividing that thing by 5. So these are how natural logarithms work, how we use natural logarithms to solve certain types of equations, and how we use e to the x to solve equations that already have a natural logarithm in them. The next thing we're going to look at is we're going to start looking at some word problems that involve logarithms. Now, the good news is in the beginning of this unit, I gave you 6 formulas, and we saw how to plug numbers into the formula to deal with some percent increase problems, percent decrease, doubling, half-life, compounded interest, or continuously compounded interest. We just plugged in numbers and we got our answers. We're going to use the exact same formulas here, just in a slightly different way that you'll see in a moment, with our logarithms. I think right now, I would just like you to read through that first example. The population of a small town is 13,635 in the year 2016, growing exponentially at a rate of 4.5% per year. In part A, we're asked, what will the population be in 2021? Well, this is absolutely no different than what we did earlier in the year. Or not earlier in the year, earlier in the unit. Percent increase, I'm going to go use my formula y equals a times 1 plus r raised to the t. All I'm going to do is plug in my numbers exactly how we dealt with this earlier. I could have given you this particular part of a question earlier in the unit, and we'll have our answer. A, remember, is your starting amount. So y equals 13,635 times 1 plus, growing at a rate of 4.5% per year. I'm going to turn that percent into a decimal, so 0.045. And if we're starting this in 2016 and waiting until 2021, That means we were waiting 5 years. Your power's a 5. Go to the calculator, type that in, and because we're dealing with a population, we'll just want to round our final answer to the nearest whole number. Should have 16,991.691. We're going to round that to 16,992 people for the population. And really, I just gave you part A to just refresh your memory on how this formula works. In the homework, there may be a few problems like part A that are just like the beginning of the chapter where we plug in our numbers and we get our answer. Part B, though, is where we're going to start needing some logarithms. In Part B, we're asked by what year will the population be double what it was in 2016? Well, even though they're using the word double, this is not a doubling problem. I know that double my starting population is 13,635 times 2. I want to know how long it takes for the population to get to 27,270. I know my starting population, 13,635, times 1 plus, I know it's growing at a rate of 4.5% per year, so plus 0.045. I don't know how long I'm waiting, so this time my variable is a power. And I do know the ending population. I'm going to end with 27,270. Well, I can clean this up a little bit, and I can make this 27,270 equals 13,635 times 1.045 raised to the t, and I need to try to solve this equation. Well, I need to get my exponential piece by itself, so I'm going to go and divide both sides by 13,635. Divide by 13,635. Well, I already know what this should be. This should just be 2 because I created this number by doing double what was in the denominator. I'm going to get 2 equals 1.045 raised to the t. Actually, it might be a little bit easier to work with this if I just switch sides on this problem. So I'm going to say 1.045 raised to the t equals 2. And now you should recognize this as an exponential equation. Anytime that I'm trying to find a variable that's in my power, I need to use logarithms to do this. I'm going to go rewrite this problem in log form. Going into log form, we're going to get log base 1.045 of 2 equals t. And then you're going to go to the calculator and use your change of base formula, where you type in log 2, close the parentheses, divided by log 1.045. And I'm getting t is about 15.747. Well, I was starting in 2016. Add 15.747 years to that. That should put you in about 2031.747, which means like second half of the year, maybe about August or September or so. One more of these. The value of a television, originally priced at $899, is decreasing exponentially at a rate of 11.2% per year. How long will it take for the television to be worth only $500? This is a percent decrease problem. Y equals A times 1 minus R raised to the t. I have my starting amount. That's my $899. I have my rate, that's 0.112. I don't know the time. I don't know the power, which means I'm going to have to use some logarithms. But I do know the ending amount. The ending amount is 500. I'm going to say 500 equals 899 times 1 minus 0.112 raised to the t. Well, 1 minus 0.112 should give you 0.888. So 500 equals 899 times 0.888 raised to the t. I'm going to get the exponential part by itself, so I'm going to go and divide both sides by 899. It doesn't give a nice even number, so how about I just leave this as a fraction? And I'm going to get 0.888 raised to the t equals 500 over 899. I'm now going to go into log form. I'm in exponential form here. I'm going to write it in log form. Log base 0.888 of that fraction equals t, log base 0.888 of 500 over 899 equals t. Go to your calculator, log of, get that entire fraction inside your log of 500 over 899, and close the parentheses, divided by log of 0.888, which should give you t is about 4.939. It will take 4.939 years for the TV to decrease to a cost of $500.